Okay, thanks for your introduction. So, hello everyone. I'm Yusuke Tomioka from the Merck. I'm a senior engineer for the MSAT Upstream. Today, I'd like to talk about monitoring quality attribute and process parameters in continuous upstream processing using Raman spectroscopy. So I'd like to start my presentation. So this is today's agenda. First of all, I'd like to start to talk from the first topics about the overview of the next generation bioprocessing. So I'd like to start to talk about the next generation bioprocessing in future pharmaceutical industry. Current pharmaceutical industry are strongly pressured for cost reduction and time saving for whole drug product life cycles. To solve such pressure for manufacturing, we may propose the biocontainer platform as a conceptual project to accelerate the shifting bioproduction industry to next generation processing. Purpose of this project is including not only software and hardware development as a consumable supplier, but also as a controlling technology for facility management. We defined there are 4 key driver technologies to accelerate the development of future bioprocessing. One is the enable process intensification, and next one is the utilize the single technology and the system integration. And the third one is the improve process analytical technology, and the fourth one is the adapt digitalization and automation. This slide shows the details of our biocontainer platform about what we will focus on and what we will develop for next generation bioprocessing. In next 10 years, for moving to future production facility, we will focus on the following 5 fields, such as the process format and the analytic and the controls and the digital plant. As a current state, the process is a batch and the format is the stainless steel and the analytics is the QC method, standard QC method, and the control is most of the system are controlled by the standard system, and regarding in terms of the data, they are not much adapted. So at the end of stage, in future process, we aim to move to the continuous processing and the single-use and the cloud processing, and utilize the inline and the real-time monitoring system, and the predictable control system, and the adapter data plant, data management. So we aim to support the shifting to end state by manufacturing. And today, I'd like to update the current development about the process analytical technologies, which is support these 3 fields. And especially, I'd like to talk about the inline and the real-time monitoring. So, would you like to start a poll question?
All right, let me read out the poll question for everyone. So this says, how about the current state of ILM, inline monitoring system implementation in your country? So your choices are in process development, in pilot scale facility, in manufacturing facility, under discussion, or not focused on ILM implementation. You should see the Zoom poll on your app. Okay, so the results are showing about 13% for in-process development. No one selected in pilot scale facility. The in-manufacturing facility is the greatest at 44%, under discussion at 25%, not focused on ILM implementation at 19%.
Thanks for your answer. So I know that the current situation of the implementation for the inline monitoring Thank you, Jeffrey. I'd like to move to next slide. So I'd like to move to next topics about controlling of the CQA, critical quality attribute with the PAT tool. First of all, I will talk about the definition of the PAT as a process analytical technology. PAT is proposed by FDA in 2004, and the definition of the PAT from the FDA is the focus on enhancing the understanding and control of the manufacturing process to achieve quality by design. And PAT is also defined by the ICH Q8. So as their comment, PAT is a system for designing, analyzing, and controlling manufacturing through the timely measurement of critical quality and performance attributes of raw and in-process materials, and process with the goal of ensuring the final product quality. About the development of the PAT, Bioforum Operation Group are also discussed about it in their publication of the roadmap, which is published in 5 to 6 years before, I remember. They are discussed about it in the topics of the inline monitoring and the real-time release. So current update from the Bioforum Operation Group, they are discussed about the current situation of the PAT implementation in biopharma industry. As their update, the situation of the PAT implementation are dependent on each facility situation, because there is no standard strategy of the implementation of the PAT, and which is dependent on the each GMP environment and the each capability of the each facilities. So what will be changed if inline monitoring technology are implemented in the bioprocessing? So PAT is expected to ensure the improvement of product quality. As an example, in current cell culture processing, as an upstream bioprocessing. So currently, some of the parameters are monitored with the inline monitoring technology, such as monitoring the DO and the pH and the temperature. On the other hand, some parameters are monitored by the offline technology, such as the VCD, TCD, and the kind of the metabolite, and also the titer. Such kind of the parameters are monitored by the offline technology with the manual sampling technique. So in future, at the end of state, we aim to implement inline monitoring technology to monitor such kind of the process parameter with the inline monitoring sensor. So result of this technical update, we can achieve real-time monitoring of the process. And because of the monitoring the real-time, each parameter with the real-time, we can understand more clearly for the process. And also, if we monitor each parameter with real-time, then we can achieve automatic control for each parameters. In this slide, I will talk about the vision and the benefit of inline monitoring technology. Before to start to talk about it, I'd like to clarify the understanding of the process monitoring technologies. So offline monitoring means that the analyzer is placed remotely in an external lab building, such as a quality control laboratory. And outline means that the analyzer is disconnected, but still close to the process. Manual action by non-laboratory personnel is required. And online monitoring means that the analyzer is directly connected through the bypass, like this. And inline monitoring means that the analyzer is equipped with the probes that were inserted into the process stream. The analysis is performed inside. About the vision for inline monitoring, different the comment from the Bioforum Operation Group. Their comment there is the three key visions for process improvement. First one is the robust material characterization, which is including process control and the assurance of product quality. Second one is the hardware. Hardware will be developed to enable advanced inline monitoring, which is including soft sensor technology. So third one is the software. Software will be developed to enable the multi-variate analysis and predictable modeling and closed feedback control. Through this next process improvement approach, we aim to achieve a following benefit in next 10 years. First one is the real-time release or product release while 1 or 2 days. Another one is the improve the product quality and operational efficiency and reliable supply. So in this slide, I will discuss about which unit operation have an improvement potential by adopting inline monitoring technology. In this analysis, priorities were ranked for each process parameter and the quality attribute. Ranking criteria and weighting is described here. Each criteria were multiplied with weight, then scored or estimated. So as one of the criteria, Q indicates where the inline monitoring technology contributes to each quality, and R indicates whether the inline monitoring will be contribute to release of the final drug or intermediate. And C indicates whether current test method have any problem and whether need to improvement. Right side table shows the result of their ranking for each unit operation and each parameter, unit operation and each parameter. Colored one is a high priority, and yellow one shows the medium priority, and the light yellow shows the low priority. So if we focus on the upstream processing, we can find many of the parameters ranked as a high score, high priority, and some parameters are considered as a critical quality attribute. So implementation of the inline monitoring technology to upstream processing are considered as a high impact on process improvement. So how much benefit are expected if inline monitoring technology are adopted in bioprocessing? In this slide, I'd like to introduce a case study about the estimation of the cost benefit if inline monitoring technology are implemented. So this graph shows analysis for the cost saving if inline monitoring technology are implemented to detect each process parameter. They are evaluated for the detection for the amino acid, charge profile, and aggregate, and the glucose. The highest benefit is estimated in inline monitoring for the amino acid monitoring, and the estimated cost benefit for the saving are $280,000 per year. And the second one is monitoring the charge profile. Third one is the glucose. Fourth one is the aggregate. They also estimated the payback period for the inline monitoring in their model case. So to implement the inline monitoring technology will be cost a very high investment. But as their analysis, the investment can be paid back during these years. In case of the amino acid case, the payback period is estimated in 3.79 years. And also they evaluated other parameters such as the charge profile, aggregate, and glucose. Such kind of the parameter, in case of such kind of parameter, the payback period is around 6 years. So this data shows the implementation cost for inline monitoring is significantly high. But if we reduce the other annual cost, then we can expect payback them in short period. So as the next discussion, I'd like to talk about the development of the monitoring technology in upstream processing. Here is a summary of the process parameter and the quality attributes in upstream processing. In terms of the pH and DO, they are considered as the critical process parameter, as a CPP. This parameter is currently monitored with the inline monitoring technology with the feedback control. And next, another parameter such as the glucose, metabolite, and the cell number, VCD. Such kind of the parameter is currently monitored with the at-line or online monitoring technology. But in the near future, to monitoring this kind of the parameter is shift to the implement the inline monitoring technology, such as the Raman or the NIR. So to monitoring such kind of the parameter is available for the Raman technology. Other parameters such as the vitamin and amino acid and the titer and the protein characteristic. This parameter is currently monitored with the offline monitoring technology. And in near future, to monitoring such kind of the parameter is moved to monitor by the online technology, such as the UPLC and intact mass. So this kind of parameter is considered as a critical quality attribute and challenging for the implementation for the Raman technology. Here, I will introduce a recent technological update in published science literature about the process monitoring with the Raman spectroscopy in continuous processing. In terms of the amino acid monitoring in continuous upstream processing, it means the perfusion cell culture. So each multiple amino acids are well monitored using a Raman system. And in terms of the accuracy, the estimated error value is around 7 to 70% compared with the max value of the range. In terms of the charge variant, also this parameter can be monitored with Raman technology, and the estimated error value as a root mean square error prediction is around 1.5 to 2%. In terms of the monomer, so this parameter is also can be monitored with the Raman technology, and and the estimated root mean square error prediction is around 0.7%. So monitoring the CQA with the Raman are feasible, but further technical updates are expected, such as to improve accuracy. So we'd like to start the next poll question.
Yeah, let me read the poll question offered. So it says, what is your highest expectation for ILM technology? Reducing risk of at-off sampling by manually, automated process control, simultaneous monitoring of multiple parameters in real time, reducing the cost and time for quality testing, and lastly, integrated process data management in digital. Okay, the results are in. Let me read it off for you. So we have a tie. The top one is tied with reducing risk of at-off sampling by manually, and tied with integrated process data management in digital, both at 30%. At 20% automated process control. 15% voted simultaneous monitoring of multiple parameters in real time. And coming in last is reducing cost and time for quality testing at 5%.
Thanks for your answer. So very interesting result. So Thank you, Jeffrey. I'd like to move to next slide. So, as the next topics, I'd like to talk about the integrated system as a PhD platform for bioprocessing. So, I'd like to start from the basic of the Raman spectroscopy technology. Talk about this. What is the Raman effect? Raman effect is the incident photon on the substance excites the vibration mode with the molecular bond. Each vibration mode results in the shift of the emission of photons at the different wavelengths in respect to the incident light characteristics. And the shift provides the information associated with the vibrational, rotational, and other low-frequency transmission in molecules. So this is an example of the water molecule. Water molecule have a 3 vibration mode. One is the bending, another one is the symmetric stretch, and the other one is the asymmetric stretch. If the laser is emitted to this molecule, then the Raman signal is response from this molecule. Then, as each vibration mode, the reflected Raman signal wavelength is a difference. So observed Raman signal, Raman spectrum is come to be like this. This is a very specific wavelength pattern for the water molecule. So Raman spectroscopy technology enabled to specify a molecule by analyzing the Raman shift in signal spectrum. So in terms of the implementation of the Raman technology in upstream bioprocessing, as you know, the current upstream bioprocessing means the cell culture, but the cell culture is a mixture of the multiple components, such as the nutrients from the cell culture media and the cells and the debris from the dead cells. So Raman spectra is a complex with a multiple molecular fingerprint. So Raman spectral key feature of the Raman spectrum is the high chemical specificity and low water interference and non-destructible monitoring system. But to detect the to monitoring the process, Raman spectral technology have a challenge, such as the signal noise interference and the spectrum data analysis and the macromolecule and the non-linear system. To solve this challenge, we need to update some technological update, such as appropriate data preprocessing approach and develop higher reliable chemotic analytic technique and build a higher accurate model building. So to solve each challenge, so recently Merck provided a new Raman analyzer as a ProSelix. So the name is the ProSelix Raman analyzer and the Bioprocessing PhD Raman software as a companion software. In terms of hardware for the Raman spectroscopy system, this ProSelix is designed for the inline and the real-time analytics monitoring of bioprocessing, and the key feature is the GMP-ready and user-friendly interface and easy to deploy the PhD solutions. In terms of the software, we can serve a Bioprocessing PhD Raman software. This software is the integrated software for the calibration batch data acquisition and the chemotic modeling and the process monitoring. From the next slide, I will demonstrate some case studies about the process monitoring using a ProSelix Raman analyzer for continuous processing. So here we would like to start a third poll question.
Let me read this one out. This says, what is the uncleared factor for implementation of ILM technology? Effect of operational cost reduction for your process, implementation method in manufacturing scale vessel, difficulty of understanding for chemometric analysis software, quantitative accuracy for the target molecule, and contribution for titer improvement. Okay, the results are in. The top choice is split between three, actually. Those three are at 26%, or the effective operational cost reduction for your process, difficulty of understanding chemometric analysis software, and quantitative accuracy for target molecule, followed by the implementation method in manufacturer scale vessel, 21%, and no votes for the contribution for the titer improvement. Thanks everyone for voting.
Thank you for your answer. Very interesting results. So, yeah, as my previous slide, I will talk about cost reduction. So, some of the researcher is interesting in this. So, thank you for your answer. Very interesting. So, I would like to move to the next slide. So, next, I'd like to talk about one of the case study. Because in terms of the monitoring of the CQA, critical quality attribute, and the CPP, critical process parameter, in continuous upstream bioprocessing. In this slide, I'd like to talk about our case studies, experimental condition configurations. So we performed the three cell culture run. One is the N-1 perfusion culture, and the next is the N-dynamic perfusion, and the other one is the N-steady state perfusion. This picture shows our system setup. We set up a 3-liter glass bioreactor here, and collect the fresh media tank here, and supply the fresh media to bioreactor, and set up the perfusion system, and after that, set up a spent media tank here. In this study, we use the chosen GS-CHO cell line, and the protein product is a human monoclonal antibody as the IgG, and we use the Excel advanced HT perfusion media as a cell culture media. And the perfusion condition, we use the silicon cell retention device for the perfusion operation, and the CSPR was set on the 20 picoliter per cell per day. For this perfusion process, perfusion setup, we also set up an inline analyzer. We use the ProSix Raman analyzer, and to monitor the Raman shift, we use the Bioforce PAT Raman software, and for analytics, we use the Bioforce PAT Chemometric Expert software. Here is a condition for the Raman spectral acquisition. Totally, we perform 11 perfusion cell culture run. It is including 6 number of the N-1 perfusion, and 4 number of the N-dynamic perfusion, and 1 multi-step N-steady-state perfusion. Each perfusion run was performed during the 7 to 21 days, and spectral acquisition was performed every 50 minutes. So, as our initial study, we performed totally 3 N-1 perfusion culture to develop a chemometric modeling. In our initial study, we tried to monitor each CPP and the CQA. As a CPP, we evaluated the cell and the protein product and the metabolic profile such as the glucose, lactate, glutamine, and ammonium. And as a CQA critical quality attribute, we evaluated the product quality and impurities such as the host cell protein and the DNA and the aggregate and the glycosylation and the protein product intact. This slide shows the result of our initial study. Left side figure indicates a flowchart about how to estimate each evaluation key parameter. So totally, we acquire the data set from the 3n-1 perfusion run, and it is defined as a complete data set. The data set was divided into two sets. One is the calibration set, another one is the test set. From the calibration set, we develop a chemometric model and estimate the root mean square error and the root mean square error cross validation. And in terms of the test set, we estimated the root mean square error prediction as a validation. So in the initial study, we monitor the critical process parameter. So each parameter is the TCD, VCD, and the IgG titer and the other metabolite. And for this evaluation, we acquire the totally 80 to 100 number of the data set from the 3 culture batch. And we estimated each root mean square error as the estimation and the cross validation and the prediction. And to evaluate each accuracy, we estimated the max value percent error compared with the root mean square error prediction. So in terms of the TCD and the VCD and the glucose monitoring, the error value is estimated around 3% compared with the highest value of the range. This error value is very low. It means a very high accuracy. But on the other hand, other parameters such as IgG detection and the lactate detection, the error value is around 7 to 8%. And in terms of the glutamate, ammonium, and osmolality, the error value is come to higher, more than the 10%. So it means that the detection accuracy is really dependent on the target molecule. After developing a model from the initial 3n-1 perfusion batch, we evaluated the real-time monitoring for the new perfusion batch as the n-1 perfusion culture A. This slide shows the result of our study. We evaluated each critical process parameter, such as the VCD, TCD, and the IgG titer, and the glucose, lactate, and aluminum. And the blue line shows the inline monitoring value using a Raman spectroscopy, and the red dot shows the values from the offline analyzer. And the pink area shows the range for the calibration batch. So from this result, the Raman system is Raman system predicts very high accurate with for the process monitoring. Next, this slide shows the result of the real-time monitoring for the other new cell culture batch as the n-1 perfusion culture B. We achieved a very similar result with the previous study. So, Raman spectroscopy can predict very successfully for the process parameters such as the VCD, TCD, and other parameters. This slide shows the result of the chemometric modeling for the quality attribute. To detect the impurities by Raman is challenging compared with the other process parameter because these concentration in cell culture is very lower. So effects for the intensity of Raman signals are masked by other higher concentrated molecules such as the glucose and the cell numbers. So this slide table shows the result of our monitoring result for to detect each impurities such as the HCP and the DNA and the antibody monomer and the aggregate and the charge variant. To estimate this result, we performed totally around 60 to 80 number of the data set, and we also evaluated each root mean square error for the estimation and the cross validation and the predictions. And we also estimated the error value percent compared with the root mean square error prediction. So in terms of the HCP and the DNA monitoring, the error value is lower than compared with the other component. The error value is around 5%. But in case of the other parameters, such as monomer detection and aggregate detection and charge variant, each error value is come to be over 10%. So the accuracy for the detection is really dependent with each parameter's characteristics. Next slide, we also evaluated the real-time monitoring for the other new N-1 perfusion culture to monitor the quality attribute. The cell culture line is named N-1 perfusion culture C. In this result, we achieved a good result for the prediction with the Raman spectroscopy systems. Blue line shows the inline monitoring result, and the red dot shows the offline sensor monitoring. This line shows the result of the model building to monitoring the protein glycosylation profile. So protein glycosylation pattern is a very low concentration compared with other parameters such as the IgG and glucose. So it seems very challenging for the implement the Raman technology. In this study, we also performed the totally 60 number of the data set and estimate the root mean square error for the estimation and the cross validation and the prediction. Then we estimated the error value compared with the root mean square error prediction. Then the error value is around come to be 20%. So lower, it means the lower accurate compared with the other process parameters. We also evaluated a new perfusion run to monitor each glycosylation profile. So I think there is some errors compared with the other parameters. We also evaluated the protein product intactness. It means the protein state of the in the cell culture fluid. So for this study, we also evaluated the totally 60 number of the data set and estimated each root mean square error. And the error value is come to be around some error value is come to be over 10% and 20%. So I feel that monitoring the product intactness is a very challenging for the Raman spectroscopy technology. So here we performed real-time monitoring for the N-1 perfusion culture using 3 N-1 perfusion culture run. Using this data set, we created chemotic modeling and applied the new cell culture batch as an N-1 perfusion culture. And from the next slide, I will try to apply this chemotic model for the other cell perfusion mode, such as the endodynamic perfusion and the end-stage perfusion. And after that, we get a new data set from each kind of the cell culture run. Then we can make a new chemotic modeling using these kind of data set. And after that, apply this new chemotic modeling for the new cell culture batch. This is the result of the monitoring the endodynamic perfusion run using chemotic modeling, which is derived from the 3N-1 perfusion culture. So it means that we didn't perform a recalibration. In this study, we evaluated monitoring the performance of the monitoring for the VCD, GCD, and the glucose and other parameters. And the blue line shows the monitoring result with the Raman technology, and the red dot shows the offline sensor monitoring result. During the early state of the perfusion culture, we achieved a good prediction with the Raman technology, but on the end of the culture, the monitoring is not much good. I guess because of this range is not supported by the calibration batch. And also during this evaluation, we missed the operation, so the osmolarity was increased. But this Raman spectral, the inline monitoring result is not followed it, this error. Maybe this is because of the result of this chemometric modeling is not suitable for the osmolarity detection. So we also evaluated the N-steady state perfusion culture using a chemometric modeling derived from the 3 number of the N-1 perfusion culture. We found a similar situation with the previous slide. In the early phase of the culture, at the low cell density condition, the prediction is successfully done, but in the later phase, which is not supported by the N-1 perfusion culture, the error value is higher. As a last case study, we are compared the inline Raman monitoring with the outline analyzer. In terms of the chemometric modeling of Raman developed using all of our previous studies, it means that the data set including 6 number of the N-1 perfusion run, and 1 N-dynamic perfusion, and 1 N-steady state perfusion. And we are also evaluated compared with the Raman spectroscopy with the outline monitoring system using automatic sampling systems. This slide shows the result of our latest study. So in this study, we use chemometric modeling, which is derived from the all perfusion run, including N-1 perfusion and N-dynamic perfusion and N-steady state perfusion. So from this result, we achieved a good prediction using a Raman spectroscopy system. Blue line shows the result of the Raman spectroscopy, and the red dot shows the result of the outline sensor. So in this study, we can achieve a good prediction using a Raman spectroscopy systems. So next is a summary. Through our study for the evaluation of the Raman spectroscopy performance, the major outcome is that we demonstrated the end-to-end seamless integration of the Raman spectroscopy based on soft sensor for real-time monitoring of the CPPs and CQS in perfusion CO2 cell culture run. And as a next step and as a challenge, exploration for the strategies for improvement of variable prediction accuracy, such as spiking the target molecule and increase the data size or the develop a data analysis technique. And next, further exploration and validation for real-time monitoring of CQA and impurities in perfusion culture. And implementation of a controlling feedback loop strategy for critical nutrient automated management, and use of the Raman spectroscopy soft sensor for the enabling automated integration of the N-perfusion bioreactor. This is acknowledgement. Thanks for your contribution. And thank you. This is the final slide. Thank you for your attention.
Thank you for the great presentation. We have a few questions in the chat that I'll read off for you. So the first one reads, please let me know how do we cross validation for a PAT system if it needs to be compared to a manual or offline instrument.
So in terms of the cross validation, so this, in case of the cross validation, some of the data set is removed from the data set automatically by the PAT software. So the data set fit is removed from the automatically by the system is the and then the reminded data set, we make a chemotic model from the reminded data set, and after that, compared to the data set, fit is removed. So this is the cross-validation. So this cross-validation evaluation is automatically supported by this software.
Okay.
Yeah.
Great. The next question we have, and before I get to this next question, we do have the feedback form in the chat. So do ask everyone to fill that out. And also, we'd love to hear any more questions you have. Okay, so this last question goes, how to perform the calibration and maintenance of a PAT system?
In terms of the calibration of the PAT system, so usually PAT system, we have two meanings of the calibration in terms of the PAT system. One is the probe calibration, another one is the model calibration. In terms of the probe calibration, we are, in case of our system, the calibration is performed before the operation, and it means that checking the performance of the probe, whether the probe tube is correctly working or not. And in terms of the calibration for the chemotic modeling, it means the data acquisition. So usually, before the implementation of the PAT system for the manufacturing, the calibration data set is acquired from the pilot scale or the more smaller scale, and then make a chemotic model for the manufacturing. But we can perform acquire the data set from the manufacturing, so you can update the chemotic models during the manufacturing.
Great, thank you so much for that. Is there anyone else that has a question? You're welcome to come off of mute now if you're so inclined.